For this next lesson, we're going to take a look at absolute value functions. So the first thing we're going to do is see how the absolute value functions compare to linear functions. So if I consider the function of f of x where it's equal to x, or g of x where it's equal to the absolute value of x. Well, I can put in the values. If I know that f of x is equal to x, so my y value is going to equal to x value, then they're just always going to match. And I can graph that out on here, where I have the point of -3, -3, -2, -2, -1, -1, so on and so forth. And there's my original function. When I do the absolute value function, well, I know if I take the absolute value of a negative, it's going to become the positive version of it. So anytime that the y value was negative, suddenly, now it's positive. When it was already positive, it just stays positive. So I'm going to wind up with a function that looks like this. -3, -3, +3, -2, +2, -1, +1, and then once I get to 0, then all of a sudden they're going to wind up matching again. And there is my absolute value function. So when it says which part of the graphs are the same and which are different, and what type of transformation can be done to create the identical graph. Well, if I look at the parts of the graph that are the same, I can see that this part, when it's positive, is the same as this part when it's positive, which means that I can state that when x is greater than or equal to 0, my new function is identical to the original function, or my absolute value one is the exact same as what the linear one was. Then I can see that I have the negative part where they're not the same in this negative section. They're actually reflections of each other. Well, we've already done reflections in previous graphing stuff that we've done. We know that a reflection across the x-axis just means that it's going to have a negative y value or a negative coefficient for the function. So how can I state that? I'm going to say when x is less than 0, g of x is going to equal the negative version of f of x, or it's just going to be reflected across the x-axis. Is there any invariant point on the graph where it stays the same regardless of the reflection? Absolutely there is. The invariant point that exists is right here. When it's equal to 0, then the reflection across the x-axis doesn't matter, so at the point 0, 0, they're going to be the same. From the graph, can we explain why the absolute value relation is a function? Well, if we think back to how we defined functions in grade 10, all that needed to happen was passing the vertical line test, where if I created vertical lines going all the way through here, then there's no points that ever stack up on top of each other, which is true. So, why is this absolute value relation a function? It passes the vertical line test. What is the shape? Well, we can say it makes a V shape. So it looks like the letter V. If you could sketch the graph of the absolute value using two linear functions, what would they be? State the domain and range of each function. Well, I'm going to split it up into the two parts. We said that it looks like the positive version. When we take a look back up here, it's the same as the positive version of my original function when it is greater than or equal to 0. So I can state that it would look like x if x is greater than or equal to 0. It looks like the reflection of it when it's less than 0, and we know the reflection of x is going to be negative x if x is less than 0. If I want to state the domain and the range of the two functions, I'm going to split it up on a little chart here. And I'm going to say that I have my domain and my range. And sorry, let's split this up and say that this is going to be my first function for f of x, and here's going to be my g of x. Well, for the f of x, the domain it's represented by x, and x has no limitations other than it has to be a real number. Same thing with y. It's represented by y, and y just has to be a real number. When I look at my g of x, it keeps moving to the left, keeps moving to the right. So x just has to be any real number. When I look at my range or my y values, obviously once it hits that 0, it's going to reflect back up, so it has to be positive. So we can state that y, where y is greater than or equal to 0, where y, e, r. And there's my range. So for the terminology we need to know, an absolute value function where y is equal to absolute value of x involves the absolute value of a variable. So the absolute value, there has to be a variable inside of the absolute value. If we talk about piecewise function, that is what we did in the last part. It's composed of two or more separate functions or pieces, each with its own specific domain that combine to define the overall function. So this was like that first example we looked at, where we said that the absolute value of x is going to look like x if y is equal to x if x is greater than or equal to 0, or negative x if it is less than or equal to 0. So we split the two linear parts of the graph into their own linear functions, and then just state what values of x would represent that. An invariant point is a point that does not change in the transformation, where it's going to be the point where the two parts of the transformation connect with each other. So, if we are graphing an absolute value function in the form of y is equal to the absolute value of ax plus b, or in this case, 5x plus 2. The first thing we're going to do is we're going to determine the y-intercept and the x-intercept. Well, I can say that if the y-intercept is when x is equal to 0, then y would equal the absolute value of 5 times 0 plus 2, which is just going to be the absolute value of 2, or 2. For the x-intercepts, then 0 is going to be y is equal to the absolute value of 5x plus 2, which means that 0 is just going to equal 5x plus 2. Negative 2 is going to equal 5x, or negative 2 over 5 is going to equal x. And there's my x-intercept. Now, it wants us to sketch the graph accurately on the grid below using the original function y is equal to 5x plus 2. So if I am sketching the graph using the slope and the y-intercept, then I'm going to start at the point of positive 2, which is the y-intercept, and then it says that it has a slope of 5, so then I'm going to go up 5 over 1, or I'm going to go down 5 and left 1. And this would be my original function. Y is equal to 5x plus 2. Now, what's going to happen is we know that as soon as it hits that point of 0, the absolute value function is going to reflect back up to the positive. So where this is negative 3, it's going to become positive 3. Where this was negative 8, it's going to become positive 8. So the negative side is going to be a reflection. The positive side is going to be the same. And there is my y is equal to the absolute value of 5x plus 2. We're going to state the domain and the range of this. Well, my domain is going to be x where xer. And my range is going to be y, where y has to be greater than or equal to 0, or y-e-r. When I'm expressing this in piecewise function, I'm going to state that for the function y is equal to the absolute value of 5x plus 2, I'm going to split it into its original form, 5x plus 2, and when is that the case? That is true in the positive region where it matches up with the original function. So I'm going to say when x is greater than or equal to what the x-intercept is here, we already solved that, negative 2 over 5. It's going to be the negative version of this. So negative of bracket 5x plus 2 if x is less than negative 2 over 5. And there's my piecewise function.